Welcome to Ask and Learn.
In this problem, we have a block here that's attached to ground through a spring. If we draw a free body diagram of the block, we have its weight and a normal force from the surface that counteracts the weight. It's not moving vertically, and it's sliding without friction on this surface here. There's an external load F acting on it, and then we have the force in the spring acting on the block also. And so I'm calling this positive x. And so this is the displacement of the spring here, or the change in length of the spring, is also going to be x. So free body diagram here says F minus Fs must be mx double dot. Fs is x times, or k times x. So our equation governing the motion becomes mx double dot plus kx equals F naught cosine capital omega t. Now, in the book, they use a little omega here, and I used to do that, but then after teaching a class that's focused purely on vibrations for many years, I realized students would oftentimes forget to write omega n, or they'd forget the n or not see the n here, and then they'd get omega, and then they'd get confused between omega n and n. So I decided just to use a capital omega here. So this is the forcing frequency. I'm going to always use capital omega for it so that it's very distinct from the natural frequency, which is a little omega n. We can then divide through this by m, and so we get x double dot plus omega n squared x equals F naught over m cosine omega t. Now, they ask for the general solution of this equation. Well, the general solution consists of a homogeneous and a particular solution. The homogeneous solution, as you can kind of see derived in the book, is harmonic, so waves oscillating in time with two unknown coefficients here, which you'd use initial conditions to solve for. So you need an initial condition on the displacement and the velocity, and then you could solve for these. Then you also have a particular solution. So this solution satisfies the equation when this is 0. This solution satisfies this equation in particular. So to satisfy a particular solution, we can really just plug in cosine omega, some amplitude, say c cosine omega t into here. And we see we get cosine omega t everywhere, and since that has to be true for all time, we can cancel out the cosine omega t, and then we get an algebraic equation that we can then use to solve for the c that the amplitude we had here. And if we do that, we'll find that c is given by this expression where I've defined some things here. Delta static, which is F naught over k. And I call it delta static because if you just had a static load of F naught on here, this would be the displacement if there was no dynamics, right? And then I have r squared here, and r is what I call the frequency ratio, and it is the forcing frequency to the natural frequency. So you can see here clearly that when r is 1, then things amplitudes get very large. Not instantaneously, they don't get large. In fact, the solution breaks down when omega equals omega n, and we have to what we wind up with then is a linearly growing particular solution in time. So it doesn't immediately explode to an infinite, but it linearly grows with time. So in steady state, it is infinite, but it doesn't get there instantaneously. The amplitude continues to grow and grow as time goes on. So you can't really say that the amplitude is infinite when r is 1, because basically the solution breaks down there and you have to get a more generalized solution. Anyway, so this is, and then if we want, we really should, our total solution is a homogeneous solution plus our particular solution. And one thing you need to be careful about is we need to solve for A and B using the total solution, not the homogeneous solution. So these will be different if the particular solution isn't 0. So we need to make sure that we apply the initial conditions to the total solution x here.